Hello and welcome to Maths on the Move, the podcast from maths.org. I'm Rachel Thomas. It might not be obvious to you, but every day maths is impacting our lives. And mathematical models, these ways of mathematically describing the world around us, they're used to inform policy decisions about the economy and public health, to understand climate change and how we could best respond to it, even designing buildings and public spaces or to try and understand and prevent crime. And if you'd like some idea of how these particular models work and more on what mathematical modelling is, we'll put some links to those in the show notes. So what all these examples I've listed have in common is that not only do the areas involved impact us in our lives, we're also part of these areas and we shape them. So whether it's the spread of diseases, the economy, the climate, our public spaces, they're all affected by what we do as people in those systems. So it seems reasonable then that the mathematical models in question should reflect the interaction between people with each other and between us with our environment. But that's actually a really hard thing to do. So some researchers are trying to do this through a fascinating new approach that involves members of the public with actually building the mathematical models from the beginning, and it's called co-production. So my colleague Marianne Freiberger recently talked to Liz Fearon, an epidemiologist at the University College London, who is also a member of the Juniper Partnership, who we have an ongoing collaboration with. Now, Liz is in the process of setting up one of these co-production projects, which she hopes will pave the way for this approach in the modelling of infectious diseases. The main idea really is to find out how the disease that's being modelled affects the people involved and to take this effect into account when you're building the model. And hopefully that means you'll result in better models that give better information about what course of action you should take when an infectious disease threatens to turn into an epidemic. But also, it's hoped that this is a more inclusive approach that doesn't leave traditionally underrepresented groups on the sidelines in public health decision making. Marianne spoke with Liz, and to set the scene for how this ambitious approach might work, Marianne started out by asking Liz what mathematical models are used for in epidemiology.
Mathematical models have been used sometimes particularly early on in an epidemic to try and make the most of relatively sparse and biased data that's seen early on in an epidemic. They have been used to explore a range of what-if kind of scenario planning exercises. So if we're trying to understand what kind of policy choices might lead to different kinds of transmission or epidemic trajectory outcomes, given a range of different assumptions about things that might happen and things that are true about the transmission process, then we can use models to try and look at what the outcomes of different kinds of policy decisions might be. And we can also use models to try and make very short-term, I would say even update our understanding of the current epidemiological situation, because it's very hard to observe infections as they occur. So even just estimating what exactly is happening right now can be a complex process. So I would say that those sort of three broad areas are how models are used in supporting epidemic response. The reason that we do this is that transmission is a very complex process that involves a lot of different moving parts, and it's not so straightforward always to intuit what might happen given different policy decisions or given different assumptions about an infection or about population contacts that underlie transmission. And the use of a model allows us to ask questions about this process in a way that enables us to better interpret the outcome, because we can ask questions one at a time, vary one aspect of the system one at a time, and that allows us to understand more about the processes underlying transmission.
Now, during the COVID pandemic, you worked on something called test, trace, and isolate. Could you just remind us what that was, test, trace, and isolate?
Yes, so we had a project to look at testing, contact tracing, and isolation policies. Testing and contact tracing and isolation are key epidemic response interventions where we try to identify people who might be infectious and able to pass on the infection to others and facilitate them to isolate away from others to whom they might pass the infection. And by this, we're trying to prevent the more widespread transmission within the population. So it's a complex intervention because there's a whole series of steps over which people need to be supported to recognize symptoms, for example, to access a test, to take a test, interpret it correctly, to isolate and to take the steps that they need to isolate at home, as was the case for COVID in their lives. And then they list the contacts that might have been exposed to their infection at a time when they might have been infectious. And then we try and trace those individuals and facilitate them to quarantine at home away from others in case they have had the infection and are also infectious to others. So it's about trying to break those chains of transmission. And in contrast to, you mentioned lockdowns, in contrast to that kind of approach, it's much more specific because we're trying to identify only those who actually have the infection and might be able to pass it on to others, rather than a lockdown, which essentially prevents contacts between everyone in the population. So where it can work, test, trace, and isolate could hopefully be less sort of associated with some of the harms of lockdown because it's a much widespread intervention.
How was mathematical modeling used in the context of test, trace, and isolate? Like, what questions were you looking to answer with it?
So quite early on, there was work to understand from ourselves and from others the potential that test, trace, and isolate had to reduce epidemic growth. So given what we knew about the epidemiological characteristics of SARS-CoV-2, so for example, what we knew about the basic reproduction number, what we knew about the timeline of infection and the generation time, would it be feasible to use a TTI-led strategy in order to to turn around epidemic growth in a growing epidemic? So there was work early on that tried to look at that, which found that really, for that to be possible, you would have to achieve an extremely high-performing test, trace, and isolate system, one that identified a very large proportion of people who had the infection, a very large proportion of their contacts, and were able to do so and facilitate them to isolate quickly. And as time went on, we looked at the use of TTI at different points during the epidemic to understand the role that it might play in preventing or slowing epidemic growth alongside other interventions, such as with a particular background of social contact restrictions. We were also asked to look at a range of different design decisions for test, trace, and isolate. So for example, decisions about asking contacts of cases to take daily lateral flow test rather than to isolate at home, and what effect that might potentially have on epidemic growth. And then some more detailed questions about what if people tested every 3 days, every 4 days. So we could try and look into some of those questions. But one of the key things that we found early on, once we started modeling, well, anything to do with interventions, was that you have to start making assumptions about what proportion of the population is able to take up those interventions. So very early on, we need to estimate if somebody has symptoms, and we could come up with some estimate for what proportion of SARS-CoV-2 cases have symptoms, how many people are going to recognize those symptoms and be able to access a test, and how long will it take them to do that? And how many people are going to be able to immediately isolate at home with all their family members? And what proportion of people overall will be able to do that? Or will some groups be able to do that and some groups not? And you have to include all these assumptions in your model of the test, trace, isolate process. And absent any other information, you might tend to assume, well, everybody fully adheres to all policies over time, isolates for the full period of time. But we know that that's not a very realistic assumption to be making at all. And so actually it worried me that we might have, if we made that kind of unrealistic assumption, we might think that policy A is better than policy B, but in actual practice, policy B might be better if we had a more realistic understanding of how people were able to interact with the interventions and policy decisions that were being made.
So what did you do? Did you then go and speak to people to find out more?
Yeah, I mean, we did. So we had a behavioral scientist who was involved in our project, and we were able to access some of her expertise and also her suggestions of behavioral surveys that were also being done, such as the Coursera study that was being done where members of the public were asked about their adherence to behaviors. So we tried to reach out to other behavioral scientists, and we tried to work from what empirical data that there was. But to be honest, in practice, it was really challenging to incorporate even that kind of information into the modeling that we were producing for the scientific advisory channel process, because we were asked to do that often over very short timescales, and we needed to present information in a very condensed format very rapidly. And the more dimensions of non-uptake or non-adherence, it's much easier to model 100% adherence to something than it is to model different kinds of non-adherence. Because, for example, if somebody is unable to take up isolation because of work pressures, does that mean that they never take it up at all? Or does it mean that they initially take it up and then halfway through they have to drop it? Does it mean that they try and reduce their contacts, but they keep going into work? And all of those things are different assumptions about how people are interacting and behaving with that policy that might have different epidemiological implications. But informing and then representing that myriad of possible outcomes was difficult to do in the context in which we were working.
Okay, so this brings us into this whole realm of thinking about building mathematical models with the involvement of people who belong to a group that would be affected by whatever disease you're looking at. So that's the idea of co-production, right? Like it's fascinating. Can you tell us generally what co-production means?
Sure. So co-production is a type of public participation or involvement in research. And in some respects, it's probably the most intensive type, where members of the public who are part of the affected population of your research, which in the case of COVID-19 was a very broad population, a broad definition of the population, but members of the public are involved from the beginning in the development of research and research priorities and throughout the whole research project as equal and equally valued team members. So that is the most sort of intensive form of public participation. You might have other kinds of public involvement where members of the public are involved at particular stages, or they're asked their opinion or feedback on aspects of the research. But co-production, sometimes also called co-development, would have that kind of more intensive definition.
So you would literally get a representative of whatever population is affected that you would like to model, and they'd be there with you from the start in this most intensive form. So, so they'd even help to decide what questions are the important questions to ask.
Yeah. And I think being involved in that very early stage, because essentially the questions that we're being asked are questions about different public health intervention design choices, actually public health objectives choices as well, because clearly kind of from an epidemiological epidemic response point of view, we're trying to essentially reduce transmission, or maybe we're trying to reduce health harms as a result of transmission, which might be a slightly different thing. But we're also balancing that often against potential harms of a public health intervention, because if you're trying to reduce transmission of an infectious disease in some completely hypothetical world, everyone would be completely isolated from each other and then we wouldn't have any disease. But clearly there's enormous harms to well-being and to everything, and that's just not practically possible at all. So I think most public health interventions, there is some kind of balance of harms and transmission aims that is happening in its design. And we really want to have broader public input into what are those harms that are experienced by the public, because as modelers or even as public health practitioners, we might not understand what those are, as well as understanding how those are balanced against the epidemiological and transmission aims.
Yeah, and I recently interviewed a couple of your colleagues from the Juniper Partnership, and they were thinking about school closures. And I guess that was a great example where you have to be really careful because the harm that it can cause educationally and on mental health and physical health wise, even on children, can be significant. So there's a real need for balance. So that would be an example then. So you're starting up, or you have started up, a co-production project. What is it? What's it about? What
Sure.
disease is it looking at to start with, and what's it called?
Sure. So in the last few months, we've started an interdisciplinary research project, which is called Co-producing Mathematical Models of Epidemics Together, so the COMET project. And our aim with this project is to develop methods and guidance and tools to enable co-production in epidemic response modeling. And as we've been discussing, part of this follows from the experience that some of us had with modeling to inform the COVID response, and some of our concerns about the need for public input into the decisions that are made when we're developing the model. And so it's really, and from our broader experience working within public health. So the way that our project is going to work is that we will have a demonstration project considering mpox. And so we are pulling together a team of co-producers, so people with lived experience relevant to mpox who are working as part of our main research team, coming to our meetings, reviewing our documents, taking part in research activities. And then we are also going to hold, along with working with some community-based organizations, some broader workshops with members of the public. Hopefully we'll be able to repeat this with the same group sort of a few times as we develop the model to get a slightly broader range of input beyond our 3 co-producers as well. And through this demonstration project, we will try and reflect on and learn about what approaches have helped enable us to take this co-production approach. And then we are going to work through our wider network, including Juniper and other partners, to test out these approaches with other kinds of infections that tend to affect other types of populations in different sorts of settings. So that's our main project aim.
Do you yet have any insight into perhaps interesting things that you wouldn't have thought of that the lived experience has told people? Are you at that stage, or are you not quite ready to have
I
those?
think we haven't started having those workshop meetings yet. We've had some interesting questions even amongst a team, who are the public who are affected by a model of mpox in the UK and responses to mpox in the UK. And mpox is a viral infection that in the UK setting has primarily affected gay and bisexual and other men who have sex with men, and transgender women to some extent. And so we had been thinking about for recruiting amongst that group more broadly. But one of our researchers says, why haven't you specifically tried to recruit amongst individuals who've actually experienced mpox infection? And I thought that was an interesting question. It prompted me to think of, to me, it was because the modeling that we were doing wouldn't be focused only on the experience of having the infection, but of everyone who was essentially subject to public health interventions to control that infection. But I thought it was an interesting and good point in that in a lot of situations, it's not necessarily going to be immediately obvious about who is the public, which members of the public need to be brought into the process. I mean, I think in further thinking as well, we might want to think about groups who tend to be underrepresented in public health decision making. And for some groups that might be systematic, and we probably tend to underrepresent people from particular socioeconomic backgrounds, from minoritized ethnic backgrounds. And so we might want to particularly consider how we might be able to involve groups who are perhaps systematically underrepresented, as well as those specifically affected, depending on the type of infection. Another thing that we are doing to support that, and this could be placed also within, I think, a user-centered design approach, is that we need to understand the context in which infectious disease modelers are working, including an epidemic response, in order to understand the kinds of tools and guidance and methods that are going to be useful for them, and to understand enough about their existing process and the factors impacting and influencing on that. So we are also going to be conducting some ethnography with a couple of epidemic modeling teams to understand more about their approach to modeling? What's the kind of universe like for modelers who are developing epidemic modelers?
Yeah, that's one thing that I found so fascinating. So not only do you need to understand the populations that are affected by the modeling, but also the modelers themselves. Because so why is that? Is that because basically the universe they live in, as you put it, will automatically have an impact on
Yeah.
what they produce in a model?
Yeah, I think that's true, and it's to recognize that every discipline has a set of norms and processes and methods that it employs, and it also exists within a particular social and economic universe of particular kinds of internet of agencies and organizations and funding pressures and settings, and all of these things have bearing on the science that comes out.
And so you literally have some other anthropologists or ethnographers
Yeah.
sitting and watching some modelers, is that right? Like looking at how they work and what they do.
Essentially, it's kind of a form of, we've sort of been referring to it as they're going to be essentially shadowing some other modeling teams to understand a little bit more about what they do and how they do it. Exactly.
That's so fascinating. I think that is such a great idea. And I mean, it does. I mean, I don't want to misrepresent it or kind of misunderstand it, but the thing is, it does make me think very much about how, especially now at the moment, there are people thinking very hard about how history of science has been developed and about decolonizing it, and
Mm.
how much certain things have been shaped by the fact that scientists were from particular demographics. So it's kind of taken that into account.
Yeah,
Right.
yeah. I think that is part of it. And I think, there've been over the last couple of years more of a move within infectious disease modeling to understand aspects of inclusion and diversity within the field of modeling. And part of that is about creating opportunities for everyone, but it's also about ensuring that we have models that reflect a diversity of experiences and perspectives. Um, I think that in the development of models, there are what can seem like small decisions being made all the time, and we might see them as kind of technical decisions, but they often have bearings on how we're representing the transmission process that underlies the modeling and how people are interacting with interventions. Very difficult for one individual modeler or even a group of modeling team members to be making all those decisions without any kind of feedback from the population who's being modeled or from other kind of disciplinary perspectives. It's difficult to even recognize sometimes what is an assumption that's being made because it might just seem like a technical choice.
Like, can you give an example?
Well, so I work a lot in sexually transmitted infections and HIV. And what we're representing there are the processes by which people form sexual partnerships, which obviously have a relational aspect to them as well. And that might affect their sexual behavior within that partnership, which makes sense. So, but often the way that the model works is, I was talking to some sexual health colleagues about this, is that the model assumes that within a partnership, the frequency of sex that people might have within that partnership is the same over time, and it happens at broadly a steady rate. And people form partnerships at broadly a steady rate. And while we might have a lot of heterogeneity in the population in terms of how many partners someone might have over a period of time, it's all happening at a kind of roughly steady rate. And once you talk to anyone who's had a relationship, or studied sexual health and sexual partnerships, this isn't necessarily a very realistic assumption. And it's not to say that we always need to include all of life's complexity within a model, because part of the reason that we're modeling is that we're trying to understand, we need to simplify the process enough to understand what are the key bits that have impact on our outcomes without accidentally overlooking something that is impactful epidemiologically that we haven't included. And that really means we need a dialogue between people who understand the infectious disease dynamic side of things with people who understand the social and biological processes that underpin disease transmission.
To what extent are the people that you have recruited gonna have to get into the actual maths? To what extent are you gonna tell them, here's the model, here's the equations, and here's how it works?
I think that, so one of the problems I think with the presentation of models to the public, but also just to those outside of modeling per se, is the presentation of models as a kind of black box. And people feel and are not really encouraged to feel like they could understand how it works. And that means that models are very difficult to critically engage with. Either. I mean, I think this is true for other researchers and people in public health, as well as the public more broadly. So I think it is really important that we try and break down how the model is working to a point that will enable people to be able to engage and critique it, because otherwise, that's the heart of our engagement. But we need to find a way of doing that is accessible and inviting to people to do so. And presenting a lot of equations on a slide is probably not the way to do that. So I think this is where I think some of our work will overlap with that relating to maths communication, seeing maths communication as a two-way process where mathematicians are both trying to integrate information that isn't coming to them as maths into what they're doing, but also explain the mathematical side of what they're doing enough to enable people to engage with it who don't have that maths background.
Well, it's really fascinating. And will you come back to talk to us again in maybe 6 months or a year's time to give us an update?
Yes, I'd be delighted to, and it would be great for you to speak to some of the other members of our team, because as well as people with lived experience, and it would be wonderful to hear their perspectives once we get going. We also have people with social sciences, human-computer interaction experience, public involvement experience more broadly, and it would be good to hear from them as well, and not just me.
So hopefully we can do another podcast whenever it's suitable.
Sure, thank you.
Okay, thanks very much.
That was Liz Fearon talking to my colleague Marion Freiberger, and we're really looking forward to seeing how the COMET project develops. And we're especially interested because we think we're going to learn a lot about maths communication from that project. But that's it for now for this podcast. We'll include links to all the relevant information that we've mentioned in the show notes. We hope you've enjoyed hearing about Liz's COMET project. And if you have enjoyed it, please do recommend the podcast to a friend, or you could rate and review it wherever you're listening, because that really helps people find the podcast. Thanks for listening, and bye.